Okay, we were talking about matrix multiplication last time. And we said if you have two matrices A and B, you can define a matrix multiplication operation that gives you C, and A belongs to P cross R, and B must belong to what? Well, R cross, this can be anything, so let us think Q. And what about what is the shape of the resulting matrix? So it will be P cross Q. Okay, and the ijth element of C is given by, do you remember? K, Kj, and K goes from what? 1 to 1 to 1 to R. Okay, that's the definition. And then we started looking at a simplified version of this, which is post multiplying matrix by a column vector, right? So if you have A, you take column vector, produce another column vector. We'll again assume this is P cross R. This means this has to be from R. And what comes out is of what shape? Yes, at what shape? Okay. Well, we can apply the rule of matrix multiplication and compute each element of Y. Okay. So Y will have P elements, and each of those elements can simply be computed using this. Okay. It's just that the ith element of Y will simply be Y I1, because it's just one column. Okay. So if you do that, right, I won't get into the details. If you do that, what you will find is essentially what comes out is something like this. We can represent A as a block row. Okay. Each one of these is a column of A. How many columns does it have? How many columns does it have? A. R columns. So there will be A, R. This is a block row. Each one is a column vector. Okay. X is a column vector, and each of those elements would be x1, x2. Okay. And if you do the multiplication, what will come out is you will see Y is simply x1 times A1, x2 times A2, xr times AR. Okay. So whenever you post multiply a matrix by a column vector, the effective operation that you're doing is you're taking the linear combination of the columns of A, and the coefficient that you use for the linear combination comes from your x vector. Okay, because Y is simply x1 times, you're taking x1 amount of A1, you're taking x2 amount of A2, so on and so forth, xr amount of AR, and you're adding them all together. That gives you this. So this operation of post multiplying a matrix by a column vector is essentially a process of taking the linear combination of the columns of A. Okay. We'll now look at another simple operation called, which is essentially pre-multiplying matrix by a row vector. Let's say the matrix we are considering is B, the shape of this is R cross Q. If we take a vector, row vector, we always represent row vectors by column vector transpose. And what should be the shape of this vector? Yes, this will be 1 cross R. That is the only thing that we are allowed to multiply according to this rule. And what will we get if we multiply, if you pre-multiply a matrix by the appropriate row vector? 1 cross Q, yes. You will get a row vector which we will represent by transpose, and the shape of this will be 1 cross Q. Okay. We can write x, if you expand the x vector out, you get x1, xr, because there are r rows. Okay. Now here we wrote A as a block row. In this case, we'll write B as a block column. Okay, and each element of this block column is a row, is a row of B. Okay, how do we represent the rows of a matrix, or the convention that we will follow in this course? Right, so the first row would be B1 tilde, and it's a row, so it's transpose. B2. And how many rows do we have? R rows, so this will be BR. Okay, and if you do the multiplication, what you will find is Y transpose, which is a row, is simply x1 times x2 times B2 plus xr times BR. This looks very much like this. So essentially what we are doing here is, whenever you pre-multiply a matrix by some vector, you are taking the linear combinations of the rows of this matrix, okay, and the exact coefficients of your mixture come from the elements of this row vector. Right? That's essentially what is stated here. Okay. By pre-multiplying by a row vector, you are taking the linear combination of the rows, and here you are saying we take x1 amount of B1 first row, x2 amount of the second row, so on and so forth, xr amount of the rth row, and we add all of them together to produce this new. We'll just do a couple of examples that you can work out so that you get the hang of it. Okay, let's say A is okay. What is A times what will I get if I do this, and what will I get if I do? Just use this formula to compute this and that one, and tell me what you get. What do you get here? one? Not sure? Here, just apply this, right? Sorry? Sorry? Oh, sorry, let them say. Yeah. See, if you're doing this operation, what are you saying? You're saying I want to produce a column or column vector which has one amount of the first column of A, one amount of second column of A, one amount of third column of A. So you take the first column of A multiplied by 1, take the second column multiplied by 1, third column multiplied by 1, and then add them together. Yes? Yeah. So you will get that's it, 3 and 2. Okay, what about this one? 0 and 7, is it? 0, 7? Is that what you get? Okay. Okay. Just as a side note, let's say I want to do this operation. Okay. And I want the resultant of this operation to be the third column of A. So what would X be? What should X be for me to get the third column of A when I do this multiplication? You understand the question? Okay. I want to post multiply A by a column vector such that the product of the resultant of this product operation gives me simply the third column of A. That means the linear combination of the columns of A should only give me the third column of A and nothing else. 0, 0? Yes, 0, 0, 1. So here, if you have all the columns here, if you only want the third column, you make all the x's 0 except for the third x, x3. Okay. Similarly, if I wanted to get 4 times B1 tilde A transpose minus 1 times B3, what should x be for me to get this? Sorry, you'll have to be louder, I can't hear you. Right, so this will be 4, 0, minus 1. If you choose x transpose to be this, then the resultant operation will be this. Okay. 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 With that understanding, we'll now try and tackle matrix multiplication in its full form. Okay. First thing we'll look at is the special case, the standard inner product. Okay. You remember this? So if x and y belong to Rn, what is the definition of the standard inner product? Xi, yi, I going from 1 to n. Okay. But we know that we can view, so if both of these are column vectors, we can view them as R n cross 1 matrices, right? This, we can think of this as n cross 1, this is n cross 1. Two matrices with single column. If you see it like that, are you allowed to multiply x and y like this? Can you do x multiplication like this? Yeah, because this and this don't match, right? But if I do this, am I allowed to do that? I am, because this will be 1 cross n, this will be n cross 1. These two dimensions match, so this is a valid operation. And in fact, if you look at that definition, that's exactly this. Okay, so the standard inner product is just an example of a special case of your regular matrix multiplication. Okay. All right. Okay. With that, maybe we'll look at one more thing. So, if you remember, I had said in the previous module, so there is an inner product operation. Then I said there is also an outer product operation, and this also is a very useful operation. Okay. both the inner product and the outer product essentially involve vectors from some Rn. The inner product is simply x transpose y. The outer product is x y transpose. Okay. But before that, am I allowed to do this? I mean, essentially do the dimensions match. What is this? This is n cross 1. This is 1 cross n. So it's okay. But in the inner product case, if I did this multiplication, I get a scalar 1 cross 1 matrix. What about here? What will I get if I do this operation? Sorry? N cross n. You will actually get a matrix. You get an n cross n matrix. Okay. And that matrix, so you have your x1, x2, xn. This is a row, so this will be y1, y2, yn. You will get a matrix with n rows and n columns, and the elements are fairly simple. Okay, the first element is simply the product of these two. We do the first row. Okay. We take the product of these two, x1, y1, these two, x1, y2, so on and so forth, xn, yn, x1, yn. Okay. The second row is simply x2 times this. The third row is x3 times this. That's all. Okay. And you will find this actually agrees with the definition. Okay. Here, your R is 1. Okay. So if you follow this definition, you will find that that's actually right. So one simple way to think of this is the rows of x y transpose will simply be scaled version of y transpose, with the first row scaled by x1, second row scaled by x2, third row scaled by xn, or nth row scaled by xn. Another way to view this, the columns of the outer product will be scaled version of x, with the first column is y1 times this column, the second column is y2 times this column, and so on and so forth. Okay. Yeah. So you can maybe quickly tell me what. So if we take what will I get? What will be my outer product matrix? Well, the first row is simply 1 times this. The second row is minus 1 times this. Third row is simply 0. You can also verify the first column is 1 times this, that's correct. The second column is 1 times this, that's right. Third column is 3 times this, so 3 minus 3, 0. Here's another thing. Both x and y don't have to be from Rn. Can I do this? Let's say the same example. Am I allowed to do this? No, verify. Verify this rule. We are allowed to do this, but what will you get if you multiply this? You won't get a square matrix anymore, you will get a 3 cross 2 matrix. What will that matrix be? Right, what will be the elements of that matrix? Yes, same thing. You apply either if you're writing down the rows are all scaled versions of this. If you're writing down the columns are all scaled versions of this. So first row is simply 1, 2, minus 1, minus 2, 0, 0. Okay, so that's the outer product. Okay, so this matrix multiplication operation, there are 4 ways to view this. 4 views. Okay, the first is the inner product view. Second one is the view. We'll look at each one of them and try and make sense of matrix multiplication. First one, inner product view. This is very simple. Okay. So we have these two matrices and we get a resultant matrix that's this of size P cross Q. In the inner product view is essentially a restatement of this. The ijth element, you generate the ijth element of the matrix C by simply taking the inner product of the ith row of A and the jth column of B. Okay, is that clear? Okay. What is the ith row of A? How do we represent the ith row of A in our convention? No, the tilde notation. AI. This is the ith row of A. Okay. The jth column of B is simply Bj. That's it. The ijth element is essentially just this, and you can verify that is in fact correct here. Okay. If you write down if you write down the ith row of A, what will it look like? The individual elements. What will be the first element? A? Not A1, the ith row of A. In matrices we have two subscripts, right? The row and the column position. Here. A11, A12, A. This is P cross R, so this is A1R, A21, A2R, AP1, AP2. So what will be the ith row if I take the ith row from here and write it down there? Yes, that's it. AI1, AI2, AIR. What about the jth column of B? Yes, B1. B, R, J, right? Both of them are vectors from R, R. That means you can do the inner product operation. Inner product is simply multiply these two, and add all of them together. That's essentially this. AI1 plus B1J, that's that. AI2 plus B2J. Now we go to the next one. Column view. Okay. So for this, what we will do is we want to produce. So we want to do this operation. Okay. We will write down B as a block row. What elements will the block row have if you write B as a block row? The elements of the block row representation of B will simply be the columns of B. Okay, so this will be B1, B2, BR. Right? Is that right? No. This is BR. How many columns does B have? Q. This is wrong. Q. But each of the columns has R elements because it's from RR, because the number of rows is R. Okay. This produces C. Okay. So in the inner product view, basically tells you how to compute each specific element of the C matrix, the ijth element. The column view tells you how to compute each column. Okay. The ith column of C is simply this, is simply A times the ith column of B. Okay. Because notice the number of columns of C is equal to the number of columns of B. So as many columns you have, the number of columns you have in B will essentially give you all the columns of C. Right? And each column is given by this. Okay. So another way to think of this multiplication AB is you are producing a matrix C whose columns are a linear combination of the columns of A, and the specific mixture that you use for the linear combination is given by the columns of B. Okay, because the ith column is essentially A post multiplied by a column vector. When you post multiply a matrix by a column vector, you are taking the linear combinations of A, and how much of each column you take is given by the elements of B, right? So a matrix multiplication operation is simply, you can view this as a process of generating new columns which are all linear combination of columns of A, and what mixture you use for each new column that you generate is given by the columns of B. Okay. So the number of columns you want to generate using the columns of A will simply be the number of columns in B. Okay. Now, if you wanted to compute, let's say B was a huge matrix, right, with several columns, right? Let's say I only wanted to compute, I know A, I know B, I wanted to compute the 153rd column of C. I don't want to compute anything else, I only want to compute the 153rd column. That means you don't have to consider anything else from B except the 153rd column of B. Just the 153rd column of B and A will determine the 153rd column of C. Okay, that's the column view. Row view. Same thing. Do this. Now, instead of here we wrote B as a block row, here we'll write A as a block column and leave B as it is. And if I represent A as a block column, what will be the elements of this block column? They will be what of A? Yes, they will be the rows of A, right? So this will be A1, I suppose, AP. Okay. Okay. And again, something very similar to this. The ith row of C, this is ith row of C, is simply you take B and you take AI. Ith row of C is given by this expression. You simply take the ith row of A and pre-multiply B by the ith row of A, you get the ith row of C. And if you remember from earlier, if you pre-multiply a matrix by a row vector, all you're doing is you're taking the linear combination of the rows of that matrix, which produces another row. Okay. Just like we spoke about here, if you want to compute the ith row of C, you only have to consider the B matrix and the ith row of A, nothing else. Okay. So another way to view this is, if you say you're taking the product of two matrices, you can think of it as you generating new rows which are essentially linear combination of the rows of B. Whereas in the column view, you can think of it as generating new columns which are linear combinations of columns of A. Okay. The last one. Okay. So here we represent both of these in block notation, A and B. Okay. We represent A as a block row and B as a block column. If I do that, can you tell me what will be the elements of this and the elements of this? This is B, this is A. This is a block row representation of A. What will the block row representation of a matrix have as its elements? What is it? The columns of the matrix. A block row representation will have the columns of the matrix. So you'll have the first column, second column, and how many columns do we have? No. A. How many columns does A have? That's R columns. What about B? What will be the elements of this block column? Those will be the rows of B. That will be B1. Okay. See, for a minute we will ignore what is inside this block column and block row and block column. Okay. But if you ignore what is inside, the operation is simply you are multiplying a row by a column. We've seen something like this before, no? Where did we see something like this? Where you multiply a row by a column? Inner product, right? Right? You're multiplying a row, well, you're post multiplying a row by a column. So here again you have a row and you're post multiplying it by a column. And how is this defined? If both x and y are from Rn, this is defined as, right? You simply take the first two elements of x and y, multiply them together, second element, so on and so forth, and you add them together. The outer product view is essentially viewing AB in that form. Okay, you're essentially taking the inner product of a block row with a block column, and if you're doing the inner product operation, then you're simply taking the first elements, multiplying them together, second elements, multiplying them together, so on and so forth, and the rth element, and then adding them all. Okay. So if you do this operation, right, what you'll essentially get is you have first element of here multiplied by the first element here, transpose, plus okay. So even though in the block row and block column notation, it looks like we've done an inner product. Look at each individual element of this. Each individual element is a column post multiplied by a row. Right? This is an outer product. If you have a row followed by a column, that's an inner product. If you have a column followed by a row, you have an outer product. Right? So another way to view this this matrix multiplication AB is simply as the sum of R outer products. Okay, there are R outer products. Okay, and each of those outer products is generated by using the columns of A and rows of B. Okay, that's essentially then. It's 1 to R. Here is another very beautiful thing. The outer product view is you're taking the inner product between a block column and a block row. Sorry, I missed it. inner product between a block row and a block column, but the individual products are outer products. There is an outer inner product and there is an inner outer product. I confused you. This is an inner product. Each product of the elements is an outer product. Okay. I'm going to say this, and then don't worry if you don't understand, you can go and think about it. Here, I mean, in each of the other three notations, right, we always represented one of the matrices as a block row or a block column. Right? Here we represented B as a block row, A as a block column. Here we represented them like this. In this view, all you do is you take A, the matrix A, and you represent it as a block column. How many columns will I have? Sorry, how many rows? Sorry. Okay, that's the block column representation of A. It has P rows. And you represent B like this. P1, B2. Okay. B has Q columns. Okay. This is a product between a column and a row. That means this is an outer product. What does the outer product give me? My inner product gives me a scalar. Outer product gives me a matrix. Okay. What will that matrix be? What will be the first element of that matrix? Well, you take the product of these two, so on and so forth. If you do that, right, the first one is A1 tilde transpose B1. This will be A1 tilde transpose B2, and so on and so forth. This is an outer product, but each of the elements that it produces is an inner product. Okay? So there's some sort of symmetry here, nice beautiful symmetry. Inner product view, on the outside it's an outer product, but the individual elements are inner product. There, on the outside it's an inner product, but the individual elements are outer product. Okay? And we'll see that all of these views will come in handy in different situations later on. We will do a couple of examples so that we get the hang of this. But all these four views are equally important, and you have to be really comfortable with matrix multiplication. Because if linear independence, matrix multiplication, they're absolutely a must for you to do anything useful later on in this course. Okay? In fact, if you don't understand matrix multiplication, or at least if you're not comfortable manipulating stuff like this, then the rest of the course will be very difficult. Okay? Okay. So let's do an example. Okay. Let's first, we'll generate AB using first the inner product approach, and this, and then the row, and then the outer product, and we'll verify that all of them will give you the same answer. Okay. So let's do the inner product approach first. What will be the shape of the matrix that comes out? 2 cross 3, fine. So it does not have to be like this. Yeah. You can now use the inner product approach and tell me each of the elements of C, the 6 elements of C. What is the first element? How will you compute the first element? C11. That means it's A1 tilde transpose and B1. That means this, you take the first row of A, first column of B, and you take their inner product. What do you get when you do that? You can tell me, you can compute all the elements and then tell me. What is the first one? 2. Okay. 3. Minus? Minus 2 or minus 1? Minus 2, okay. We can correct it later if it's wrong. 3 is in. Standard product. Let's do the column view. Maybe I will run out of space, so let me rewrite this. Inner product view, we get what? Can you repeat it? 2, 3, 3. Okay. Now sorry, where is 7? 7. Okay, alright, let's do the column view. So here, you don't compute the individual elements, but you compute the first column of C, second column of C, third column of C, and so on and so forth. And then you tell me what, once you compute each column, you can tell me what you get. How will you compute the first column of C? You simply take A and you only have to consider the first column of B. You don't have to consider anything else.
In column view, if I have to know like the quantity of columns,
Yes.
I can use this, but where would it come from?
Where would it be useful? Oh. I can't think of an immediate application where it would come up. Not sure, but I'm sure there is some place where it comes in handy. Okay, yeah, you have it. What is the first column? Well, you could have just said 2 minus 2, but don't do that. Compute it and then tell me. 2 minus 2, is that okay? Second column? Three nine, okay. Okay, here, do the same thing. Now you'll have to use the rows of B and simply use the first row of A to compute the first row of C, second row of A to compute the second row of C. What is the first row? Yes, it will be 2, 3, 5 because you're taking just the sum of the first two rows of B. You're not considering any part of row 3 of B. What about the second? What about the second row? That's fine, right? It comes out to be okay. The last one, what I want you to do first is to compute each of these inner products. Okay, how many each of these outer products. How many outer products do we have here? We have R. How many will we have here? In this particular case, A and B. 3. Yeah. Tell me each of those outer products first. So we'll first compute A1. B1 tilde transpose. And what shape will each of those matrices be? Each of those outer product matrices. Well, you don't have to think too much. The result is a 2 cross 3 matrix. The only matrices which you can add and produce a 2 cross 3 matrix are 2 cross 3 matrices. So each of those will be a 2 cross 3 matrix. Yeah? You can tell me the 3 outer products first, and then we'll then make sure that if you add all 3 together, you will get this matrix. What is the first one? Second. To compute the first one, you take the first column of A and the first row of B. Yes. What is the first one? Yes. What is the second outer product? So that will be 1, 2. 1, 1, 4. Okay, the last one. So that will be 0, 3 minus 1, 3, 0. Okay. Okay. Now, if you simply add all 3 of them together, what do you get? You add the individual elements, you get 1 plus 1 plus 0, 2, 2 plus 1 plus 0, 3, 1 plus 4 plus 0, 5, minus 1 plus 2 minus 3, that will be minus 2, minus 2 plus 2, 9, 9, minus 1 plus 8, 0, 7. Exactly. So, all of them are the same. Okay. All 4 different ways of doing matrix multiplication. Okay? All right. There are some important properties for matrix multiplication. The only 2 things I will mention here, rest are in the notes, they are quite straightforward, and you should try and see if you can demonstrate that those are in fact true using the definition of matrix multiplication. Only 2 things we will talk about are these. First is commutative. Right? In fact, it is not commutative. If you have 2 matrices AB, this is in general not equal to BA. This is probably the first uncomfortable thing that we have to deal with once you move from real numbers. Real numbers, it doesn't matter what order you multiply them, but with matrices it does matter. I mean, you can always find examples where this is true. I mean, AB equals BA, but not equal to means in general they're not equal. That means you can find at least one example where it's not equal. So this is one important thing to remember. So you should never assume that BA and AB are the same thing, and be very careful if you have an expression that involves matrices, it matters whether you multiply a new matrix from the right or from the left. Both of them might have very different meanings and will produce very different results. Okay, that's one. And then the transpose operation, right? AB produces a matrix, and I can do a transpose operation on a matrix. That means I can take the resultant matrix and ask what is the transpose of this. It turns out the transpose of this matrix is simply, you can verify that the shapes will agree if you do it this way, and in fact AB whole transpose is simply B transpose A transpose. You can show that in fact this is true for any general sequence of matrices. Will be, you reverse the order of rotation and transpose each matrix. And the rest is distributivity, associativity and all that. Those are just standard stuff. Okay, so that's all I wanted to say about matrix multiplication. The next thing we look at is the extension of the idea of a linear function. Do you remember what is a linear function? We discussed it yesterday, I think. What is a linear function? So if I have a function f from Rn to R, when would I say that this function is linear? It might be in the note, in the summary sheet, you can refer to that. When is this function linear? Right, linear functions can be represented as an inner product between vector w and your argument x. But when is this linear? Right, maybe it's not there. So, yes, so if x1 produces y1, x2 produces y2, then alpha 1 x1 plus alpha 2 x2 must always produce alpha 1 y1, alpha 2 y2 for all possible x1 and x2 from Rn, and for all possible real numbers alpha 1 and alpha 2. If this is true for all those cases, then this function is linear. Okay? And we define linear functions as just functions of this form. You go from a high dimensional space to real number. Okay? Then you could ask, well, is there a generalization of this idea where I don't go from a high dimensional space to the real line, I go from a high dimensional space to another higher dimensional space? Okay, you can. Those have a slightly different term. Those are called linear transformations or maps. Okay. Function is reserved for something that goes to a real number. Linear function, linear transformation. If you say f is a linear transformation, you can see it goes from Rp to, or let me put it this way, Rq to Rp. Now, this is any function. Okay, this is a general definition of a function that takes stuff from Rq and then produces stuff in Rp. Okay, this does not make it linear. Okay, if you want this to be linear, if f is to be a linear transformation or a linear map, then the same thing. If the vector x1 produces vector y1, notice that x1 is from Rq, the vector y1 is from Rp. Earlier I simply wrote y1 without the underbar because y1 was a scalar. But now these are n vectors, or in fact p vectors. And let's say x2 produces y2. Okay. Then this function f is a linear map, or this f is a linear transformation or a linear map if the a linear combination of x1 and x2 produces a similar linear transformation of. If this is true for all x1, x2 and all alpha 1, alpha 2, then you say f is a linear transformation. This also implies one thing, right? If I take the 0 vector from Rq, right, and I apply this function f, which is a linear transformation, what will it produce? 0 of what? 0. It won't be a real number, but what will it be? It will be a vector from, it will produce a 0 vector from there. Okay. Earlier it was just simply 0, the real number, but in this case it's a 0 vector from Rp. We also saw that if f was linear, no, every f could be represented by this vector w, right? Because f of x was simply equal to, every function f could be represented by some vector from Rn. You can either compute the function using whatever is inside this function, or you can simply compute this inner product. Both of them, if w represents this linear function, and both of them will give you the same answer no matter what x you get. That means both of them are exactly the same. This is for linear functions. Turns out there is a corresponding representation for linear transformations, and the linear transformations are simply now if f is a linear function from Rq to Rp, the linear transformation f can be represented by a matrix A of what shape? Rp cross Q. Okay. And in fact, you will see that now linear functions are simply a generalization of this, where Q is 1. Oh, sorry, where P is 1. Okay, because W is a row vector, okay, or a matrix with one row. P is 1, then A is essentially W. So that's, linear functions come inside linear transformation. Okay. So earlier we saw matrices as simply an arrangement of numbers, but they also have another meaning, that you can think of matrices as linear transformations. That means things that will take input vector and then do some operation and produce an output vector. Okay. Okay. And every linear transformation f has a corresponding matrix which represents that transformation. Last class I said, let's say I gave you a function f that takes in a vector and returns a real number. Now let's say I give you a linear transformation that takes in a vector from Rq and returns a vector from Rp. If you know the matrix corresponding to this linear transformation, you don't have to call this function. You simply have to do matrix multiplication. Okay. So f of x in that case will simply be A times x. This is P cross Q. This is from Q. Where will the product of this be? What space? A is P cross Q. Sorry? Yeah, RP. Right? F of X produces stuff in RP as out. If A represents the linear transformation F, then both of them will be equal no matter what X you choose. Now we'll look at why matrix multiplication has this strange definition. Okay, let's say we have two functions, right? Two linear transformations. This takes stuff from RQ to produces R. Okay, you have another linear transformation that takes stuff from RR and produces RP. Okay. Let's say this function has a representation, a matrix which represents this. What will be the shape of this matrix A1? If A1 represents F1, what is the shape of A? Okay. What is it? Is it R cross Q or Q cross R? Q cross R, is it? Why? Here, go back to here. You take stuff from Q, produce stuff in P, then it's P cross Q. You take stuff from Q, produce stuff from R, that means this has to be, what about this? Let's say this is A2. Where is this from? Yes. Okay, alright. Now, let's say this is my space RQ. Okay. This is my space RR and this is my space R2. Okay. F1 takes stuff from here and produces stuff here. Right? F2 on the other hand takes stuff from here and produces stuff there. F1 is also represented by A1, F2 is always A2. Okay. Now, let's say I take an element from RQ. Okay. I can take this and I can ask, okay, what will I get if I do this? U. If I apply the first linear transformation F1 on this element U, let's say this is U. U is here. Okay. This will produce a vector in RR, right? Okay. Now, this second transformation takes stuff from RR and produces stuff in RP, right? And this is a vector from RR, so I can actually apply F2, right? Just to see what happens. So I'll take this and then I'll apply F2. And this outer operation now will produce stuff in, so here, this was in R, this is in RP, whereas this was in. Okay. And this will produce some vector V. V will be in RP. You must have come across operations like this, where you have a function, you have a variable, you apply a function, you take the output and you apply another function on top of that. Right? This is called a composition operation. Composition of, right? Where you take the output of one function and apply another function on top of that. Okay? Or in a way, you're repeatedly applying one function after the other based on the output that comes out. Right? And this is usually represented by F2, F1. Okay. This itself will be another function. Okay. Now, this whole thing, the whole thing you can view it as another function, which simply takes stuff from RQ and produces stuff in RP. It's just that inside that function you have this intermediate step of producing stuff in RR. But if I simply give you this function, right, you might not know what is going on inside, right? Inside it might be computing two different functions, but on the outside for us, this is just one function that takes stuff from RQ and produces stuff in RP. Right? This composite function. Okay? And let's say that we call that F3. Okay? So I can call F3 with U and it will directly produce V for me. Whereas on the inside, maybe the way I've written it is I first take U, I apply F1, I get an output, and then I take that and then I apply F2 and then I produce V. Okay? That's the composition operation. Okay? But if we are talking about linear transformations, right? We know that each of these, at least F1 and F2, we know its corresponding matrix representation, right? That means I can represent F1 of U as what? Well, I could have computed this using the matrix A. How would I compute it using the matrix A? Sorry, A1. Well, you simply take A1 and multiply it by U. Both of them will give me the same result. Okay? I mean, like I've written there. If A represents the function F, then F of X, this operation will be the same as A times X. Similarly here, if A1 represents F1, then F1 of U is simply A1 times U. Okay? Now, if I take this and I apply F2, right? As far as F2 is concerned, this is simply a vector from RR. Okay? The corresponding matrix for F2 is what? Yeah. A2. No, A2? Here. A2 represents F2. Right? So that means this whole thing I can simply write it as A2 times this vector, which is A1U. Okay. I've not discussed this. Matrix multiplication is associative. If you have a bunch of stuff you are multiplying, the order in which you multiply does not matter. The order in which you place the matrices matters, but I can first multiply this and then multiply the result with this, or I can first compute this and then multiply that with this. So associated, it's still associative. That means I can move this parenthesis around. I won't compute this first, I'll compute this first. Okay. And this will produce a new matrix. Okay, I'll call it A3. Okay. And that A3 is nothing but the matrix that represents F3. Okay. So another way to view matrix multiplication is you are essentially doing a composition of the linear transformations represented by each of these matrices. Okay. Either in the notes or in the slides, there is one slide that kind of explains this, goes in the details of how the definition of matrix multiplication comes about through this composition operation. We won't go through it in class, but you can take a look. If something is not clear, you can ask me. So, another way to interpret matrix multiplication is, if you think of each matrix representing a linear transformation, then you're essentially, when you're multiplying matrices, you're essentially doing composition of those functions or those linear transformations. And in what order are you composing stuff? Let's say I'm multiplying 5 matrices together, right? Each one of these represents some linear transformation. In what order am I composing the linear transformations? Is it from, let's say this is, maybe let's do it like this. Am I composing in this direction or in this direction? Right to left or left to right? Which function am I applying first, followed by some next? A1, is it? Okay. Just look at this. Well, it was A1 here because A1 was rightmost. Here, you're actually applying this first. So if I take a vector. And if I multiply this, right? We're first multiplying these two, and then the result gets multiplied by this, this, and so you're first applying f5 of u, assuming f5 represents this, and then you're applying f4 on the resulting output, f3, f2, and f5. Okay. So the order in which this vector gets transformed is from right to left. Okay. Now, this should also kind of explain why matrix multiplication has this strange requirement that this dimension or this the number of columns of A has to be equal to the number of rows of B. Okay. It's because if you think of this as composition of functions, you're applying B first, and then you're taking the result of that, and then applying the linear transformation corresponding to A. You can take the output of B and feed it to A only if they are compatible, right? Here, you could multiply a vector, A1 by a vector, get the output, and then multiply it with, apply F2, because the output of F1 is in RR, the input of F2 is in RR, right? But if this was R1 and R2, then there is a problem. This is RQ, this produces stuff in R1, this is R. They are not the same space. That means you can't first apply this and then take the output and then apply this because they are not the same space. So if, because matrix multiplications represent composition, the intermediate outputs or intermediate, the interface between two matrices have to match. That means the set in the middle. That is the reason why the number of columns of A must be equal to number of rows of B, because the number of rows of B is the output space of the function represented by B, and the number of columns of A is the input space of the linear transformation represented by A. Okay? All right. Alright, so that's all I wanted to say about linear transformations. We'll now look at a couple of, again, important topics before we conclude. Rank of. Okay. Say we have A. P cross Q matrix. The rank of a matrix A, okay, is a non-negative integer that tells you something about the matrix A. Okay. This is simply equal to the dimension of the span of the columns of A, a set formed by the columns of A. How many columns? Q columns. Okay. And this will also be equal to the dimension of span of the rows of A. Okay. Sometimes you might hear people call the dimension of the span of the columns of A as the column rank, and the dimension of the span of the rows of A as the row rank, but row rank and column rank are always equal. Okay, which is essentially the rank of the matrix. Okay. Okay. Now you have to go back to your previous module and try and understand what this means. you form a set using the columns of A. Okay? And then you generate its span. That will produce a subspace. Okay, where are the columns of A from? What space? Well, it has to be either from RP or RQ. What space is it from? The columns of A. Essentially, how many elements do the columns of A have? Q elements, is it? Think about it. Column. How many elements do the columns have? The number of elements in the column is the number of rows. That's P. So each of these is an element from RP. And if you generate the span of a set of elements from RP, you will get a subspace of RP, okay, that resides in RP. It could be all of RP, but not more, but it will be some subspace in RP. Right? You could ask, what is the dimension of that? How will you compute the dimension of a subspace? Or what is the definition of the dimension of a subspace? Maybe you'll have to go back and find out what is the definition of the dimension of a subspace. Yes, it's a number of vectors in the basis for that subspace. Okay, so this number essentially tells you the number of dimensions, or essentially the dimension of the subspace that you can produce by taking the linear combinations of columns of A. Okay, I mean, you do a similar interpretation here. Where are the rows of A from? What space? RQ, right? Okay. So you take those, you generate the subspace that you can obtain by taking the linear combination of rows of the rows of A, and then you ask what is its dimension. Okay. It turns out that both of them will be exactly equal. Okay, and that is the rank of a matrix. Okay. See, one way to interpret it is like this. Whenever we do an operation like this, right? What are we doing? What are we doing to the columns of A when we do an operation like this? Well, we're taking the linear combination of columns of A, okay, and the exact mixture for the linear combination comes from X. Okay, the rank of A essentially tells me, let's say I'm free to choose any X I want, right? X comes from RQ, right? I'm free to choose any X I want. The rank tells me, if I'm free to choose any X I want, what can I actually produce using the columns of A? Okay, for example, if I had a matrix like this, okay, I mean, X has to be from R3. I can choose X is under my control. A is fixed. Somebody gave me A, but I can freely choose X. Okay. No matter what X I choose, what output will I produce if I do this operation? I will always only produce 0. Okay. Now instead of that, let's say I had this. Again, let's say I'm free to choose whatever X I want. If I do this multiplication for all possible X's, what outputs am I likely to produce? Linear combination of these. But what will the linear combination of these three vectors give me? Well, there is a reason I've written them like this. All of them are scaled versions of each other. That means this is all three of them essentially represent one vector. Okay. So no, I can take alpha 1 times this, alpha 2 times this, alpha 3 times this. But in the end, if I do that, I will always get some beta times 1, 1. That means if I choose this matrix and I choose whatever X I want, I will only get vectors of this form. That means, that means something. That means this is in some way restricted, right? If I take this matrix and I do a post multiplication by a vector x that I'm free to choose, the output that I get will always be of this form, right? Whereas this matrix is even worse. No matter what I take here, I always get the 0 vector. But instead, if this was like this, right? In this case, you will find you can choose different possible values of x, and in fact, you can generate all possible vectors in R2 if you had a matrix like this. Okay? So this matrix in a way is nice because with this matrix I can generate everything from R2 because the output space of this matrix is in R2. Whereas here, if I had a matrix like this, even though the output space is in R2, I can only produce a 0 vector. In the previous case where this was 1, 1, minus 1, minus 1, 2, 2, even though the output space is in R2, I will actually only produce elements along a line spanned by the vector 1, 1, right? So this is maybe the worst possible matrix if you want to generate stuff in R2 using elements from R3. This is a little better because at least you don't produce 0, you produce stuff along a line, whereas this is better because this matrix will allow us to generate all possible vectors in R2 if that is our goal. Okay? And that is essentially the idea of the rank of a matrix. What dimension of a subspace in your output space RP does the matrix allow you to produce? Okay? If the rank is 0, if that essentially tells you it's a 0 matrix. Okay? The only matrix with rank 0 is a 0 matrix. That means the size of the subspace that you can produce by doing AX is of dimension 0. That means the matrix will always produce the 0 vector if you do AX. If it's of dimension, if rank is 1, you can produce a one-dimensional subspace in RP. That means if you do AX, no matter what x you choose, the resultant vector will always be in that line. If it's 2, then it will be a two-dimensional plane in RP, and so on and so forth. If the rank is actually P, that means you can produce any vector in RP because the rank tells you the dimension of the subspace you can produce by taking the linear combination of columns of A. You can also do this. Right? I can take the linear combination of rows of A. Right? The same argument applies. Okay? The dimension of the subspace that you can produce in RQ is determined by the rank of A. That's what this statement means, dimension of span of rows of A. Okay? And the rank of a matrix will always satisfy this property. Rank of A will always be less than or equal to the minimum of P comma Q. Okay? It can never be greater than either of these numbers. It can be equal but not greater. And when it is equal, when let's say rank of A equals the minimum of P cross Q, then you say it's a full rank matrix. Okay. If it's less than the minimum of P cross Q, then you say it's rank deficient. Or another term you might come across, it's a singular matrix. Okay. Okay. We have 5 minutes, then we'll quickly go through matrix inverses. We will have a separate module on matrix inverses, so I won't go into any details here. So, let's say we have a matrix that is P cross P, square matrices. Okay, and let's assume, and okay, if the matrix, if it's a square matrix that's P cross P, what is the maximum possible rank for this matrix using that? P, yes. The rank of A has to be less than or equal to. Okay. If the rank is equal to P, right? That means P is a full rank matrix. Okay. Then you can find a matrix B. Well, let's say two matrices. Two P cross P matrices, or there exists a P cross P matrix, B and C, such that B into A gives me IP, the identity matrix, and okay. In fact, I should not say A and B. Let's say just B. There is a matrix B such that if you pre-multiply A by B, or if you post-multiply A by B, you will always get the identity matrix when A is full rank and square. Okay. Then this matrix B is called the inverse of A. It's the inverse of A, and it's represented by A raised to the power minus 1. You can think of it like this. If I give you a real number 4, okay, the inverse of 4 is a number such that if I multiply that number by 4, I'll get 1. Okay, the inverse of this is 1 by 4. Give me 1. Doesn't matter, I mean, because real number multiplication is commutative, it doesn't matter what order you multiply it in. But with matrices, you have to be careful. Okay. You can find an inverse for all real numbers except what? Except 0. The same analogy applies here. When you say the rank of a matrix is P, then you're saying it's in some way not equal to 0. It's not 0. Or when it's rank deficient, in some way it is like the 0. That's why you don't have an inverse. Okay. We will see later that it actually has a left or right inverse, but it does not have an inverse, which means you can multiply it either on the left or the right, and you will produce the identity matrix. Okay. Right. So this matrix for square full rank matrices, you always have an inverse that will produce the identity matrix, and this is unique. There is only one inverse for every matrix like this. Every square full rank matrix has a unique inverse that satisfies this property. In fact, see, if the product by a square matrix and its inverse is actually commutative. One of those cases where the product of the matrices does commute. Okay. Right. Now, I mean, there are some properties that you'll have to remember. You can again look at the slide. So if you have two matrices, let's say both of them are square and full rank. Okay. The inverse of this is simply B inverse inverse. Okay. And if you have A square and full rank, the inverse of the transpose is transpose of the inverse. Okay, all right. That's all I wanted to say about matrices. Again, see, there is a lot of things that you will have to remember. Just go back and make sure you've revised it well before next week. Because from this point on, we will never come back to definition of matrix multiplication. I'll simply say you're multiplying matrices, and you kind of have to understand what that means and how you do it. Okay. Okay. If there are any questions, we will quickly discuss and then call it a day. No? Okay. All right. See you guys tomorrow.